We will see in this tutorial how to export sections and elements from standard MakeFlux to MakeFlux Pro 3D. So let's imagine that we have a project carried out in standard MakeFlux. When a pressure drop is calculated in standard MakeFlux, a line is added to the inventory of pressure drops. If the exit and entry diameters of each consecutive element correspond to each other, we have a coherent section. In this case, with the diameters and the order of the elements well established, we can export our section to MakeFlux Pro 3D. Here this section ends with a rounding elbow. We add a small section for the example. Here, the section ends with a 150 diameter elbow. We therefore add a 150 mm diameter pipe, 2 meters long. The pressure drop is calculated, the calculation sheet appears. A line for the 150 mm pipe, 2 meters long, has been added. We'll add a bend, to show an example of a singular head loss. We add a 90-degree bend, with a diameter of 150 mm. And we calculate its pressure drop. His detailed results sheet appears. And the inventory has been implemented, of an additional line for this elbow. On the other hand, there is an error, diameter 15. I made a mistake, we will delete this line. Delete the line. And we will start over. We will go here, correctly apply the 150 mm diameter, calculate the pressure drop. Here, we return to the inventory. The diameter is indeed 150 mm. We want to export to Pro 3D, so we open MakeFlux Pro 3D. There, we go back to standard. And in the inventory, we will simply click on Export to MakeFlux Pro 3D. The export function asks to save the section. Section 1. And it is saved in the library of MakeFlux Pro 3D. Now we just need to drag it in our 3D space to create a network. With this, we see our imported section. We find our elements, cones, diaphragm, and our elbow which ends at 90 degrees. We will take the opportunity to show how to orient a section. Here, we want this section to be horizontal, so we select the first element, and we will introduce an orientator. So the function of the orientators is to orient elements. Without modifying the pressure drop. We inserted an orientator, which is here. And we are going to use it to set the orientation of our section. We set the deviation to 90 degrees. And we can also adjust the orientation. Here, we have imported and oriented our section. Adjustments are certainly to be made. Double-click on an element in the tree, refocuses the screen on this element. We can orient this elbow differently. The elbows are orientable without having need to insert orientator. We modify the orientation of the elbow and set it to 90 degrees. Here we have adjusted our section. We can test a throughput. We are going to test a flow rate of 100 cubic meters per hour. Apply, so this modifies the test value. And we use the function, create a generator producing 100 cubic meters hour. The roughnesses not being defined, they are applied to the default values. And here is the section tested at 100 cubic meters per hour, which requires a pressure of 23 meters of fluid column. So we are going to see how to access the information given to us for the elements of the section. Here we have the results area with a flow. When we select an element, we update the corresponding results. So, for example, I select in the tree the section as a whole. To see the pressure variations, so the difference in level is 0. The dynamic pressure at the output, 1233, it is the dynamic pressure which was created, and which is found at the network output. So if I select the end element, we should have the same dynamic pressure, 1233. We see that the gauge pressure at the outlet is -1 Pascal. Normally it is 0, depending on the precision of the calculation. It corresponds to the atmospheric pressure. So here, the pressures are gauge, not absolute. The pressure supplied by the pump is in pascals. We can change the units. So if I select the global section, we have total pressure drops of 2.266 bars, and a pump that generates a pressure of 2.278 bars. This pump pressure corresponds to the head loss at the flow rate of 100 cubic meters per hour, plus the dynamic pressure that was generated by the pump to accelerate the fluid because it started from 0 speed. We can also edit the piezometric graph. The piezometric graph shows the balance of the pressures of our system. It shows the evolution of the pressures along the section during passage through the elements. We have show hide options to make the graph more readable. We are going to be interested here only in the losses of load. We see the evolution of pressure drops. We see here a load gain, so we are increasing the pressure. It is the pump, the pressure generator. We see in this part that the pressure drops are insignificant. In the diaphragm we observe a high pressure drop. This is the main pressure drop of the system. At the bottom of this piezometric graph, there is a data table which makes it possible to record the data for each element crossed. This is reminiscent of the inventory of pressure drops Mechay Flux Standard, plus other information, such as dynamic pressures, entry and exit speeds, which are given to analyze our section. And all these parameters are printable and recordable. We close the piezometric graph. We are going to launch a particle trajectory test. This makes it possible to simply show the evolution of the pressures and of the speeds in the ducts. So we have a pressure scale, which tells us the evolution of the pressures in the section. We see that the main evolution of pressure is in the diaphragm. We see the ballistic trajectory of the fluid particles in ejection. This can be used to visualize water jets. The parameters of the internal fluid and of the external fluid, and their respective densities, can modify the trajectory of the fluid at the outlet. If, for example, we have hot air coming out in cold air, we will see the fluid going up instead of going down, like here. That's it for this export function of sections from standard Mechay Flux to Mechay Flux Pro 3D.